Hi, fifth grade. In this lesson, I'm going to be reviewing 2 pages of notes that we previously did almost a month ago. So you don't have to write anything down, but you might want to actually have these notes out and follow along as I just go through this. This is all background information that's going to help us with the lab that we're going to do a little later on in this unit. So reviewing our sound unit, the first thing we learned is what sound actually is. Sound is a form of energy, meaning it is not matter. We talked about the idea that when God created the universe, he kind of had 2 big categories of things he created. Matter is our solids, liquids, and gases that we studied in our previous unit. And then the rest of the things he created are energy, and sound is one of those. That also includes things like light and electricity and heat. So they're not things that take up space, they don't have mass to them, but they move through matter. So sound is a form of energy, and specifically for sound, that form of energy occurs when something vibrates. So in order to have a sound produced, there has to be vibrations, and that word to vibrate just means to move back and forth. I gave you the example of a vibrating guitar string, and this little video here shows a slow motion demonstration of someone playing the guitar, and you can see in that slow frame that the guitar string is actually moving up and down and vibrating to produce the sound. Next, we looked at a number of different examples of things that were vibrating, and we identified in each one of those what was actually vibrating to create the sound. So we looked at a rubber band that makes that twanging sound. And of course, what would be vibrating is the actual rubber band, kind of in a similar way to a guitar string's vibrations. When it's your voice, I encourage you to put your hand right on your throat, and then we sang the alphabet. And you could feel that those vibrations were coming from your vocal cords. And this little image here shows from the side where your vocal cords are located and how they vibrate. And then if you were to take a camera and put it down your throat and kind of look at it from the top, that's what those vocal cords look like that vibrate. And this is a little gross, but this actually is a real video here of an actual person's vocal cords vibrating back and forth, so you can see how that works. Next, we have whistling. And in this case with whistling, it's actually air that is vibrating as it moves back and forth. If you actually try whistling, it's not actually your lips that are doing the vibration, it's the air that your lips and your mouth are pushing through that are creating the vibration for the sound. We looked at our singing aluminum rod, and I did this demonstration for you with this really annoying sound here. And that is, of course, the aluminum rod that is vibrating. And I did mention, by the way, that aluminum is particularly a good metal for conducting sounds. When we studied electricity, we talked about how metals are conductors. They pass electricity through them easily, but actually conductors will allow any form of energy to pass through them easily. So aluminum allows not only electricity to pass through it, but also sound and also heat. So metals are good conductors of any form of energy. Then we looked at our Chinese water spouting bowl here, and just flash back to this video of you all messing with it.
If you put your hand on the desk, you can feel it. Missy, I go after more. That's the bowl.
So one of the things I want you to notice with that Chinese water spouting bowl is the fact that the sound is actually traveling through 3 different phases of matter. In that one example, all 3 phases of matter have sound traveling through them. So when you are rubbing your hands back and forth over the bowl, that's a solid, the brass handles to it, and then that passes from the solid handles into the solid metal bowl. And then, of course, the sound vibrations travel from the bowl to the water, which is causing it to make those waves and spout up. And then, of course, the sound that you could hear was because the sound is traveling through the air as well. So that vibrating sound that you get from the bowl is traveling to your ears through the air. So we know that from that bowl, that sound can travel through solids, liquids, and gases. And then the last thing that we looked at was a tuning fork, and we looked at the aluminum tines, which are like the little pokey parts of the fork that vibrate back and forth. Remember, a tuning fork is used to tune pianos and other types of instruments. And it's just a piece of aluminum that's specially shaped to make a certain note. So let's flash back to this one.
Wait, I can actually get it to last thing. Wait.
And in that example, what you can see from it, what we took away from it, was that the sound travels in waves. So you can look at the sound. This is a slow motion demonstration of a tuning fork moving back and forth, and you can see how the sound is traveling in waves there. You can also see in this that it doesn't have to just be the water that's going to show those waves. It also can be traveling through air as well, and it will make those same types of waves in the air. We just can't see them in the air. We can see them a lot easier in the water. But in your notes, we came up with that big idea that sound travels in waves. And we're going to spend a whole lot of time in this unit studying different types of sound waves and how those waves look different to make different sounds. So that brings us to how we actually hear things. So if sounds travel in waves, how do those waves actually reach your ear? So we reviewed in our notes, and we gave the example of a tuning fork, that in step number 1, that tuning fork is vibrating. And then as that tuning fork vibrates, all the air molecules that are around it also start to follow that same vibrating pattern of pressing together and squeezing apart. So the air molecules next to it vibrate in step 2. And then in step 3, the vibrating air molecules near the tuning fork make the air molecules next to them vibrate. And then those molecules squeeze together and spread apart. So now further out, more of the air molecules around it are vibrating. And it's kind of like dominoes where they're passing that pattern of vibrations along. And then in step 4, the air vibrations continue to spread until they reach our ear. So that's how we're actually able to hear a sound across the room, is because the vibrations are spread through the air molecules until they reach our ear. In the next page of notes, we looked at some more specifics about waves. And we looked specifically at compression waves as the definition of a sound wave. But first, let's just give our scientific definition of a wave. It definitely is a science-sounding description. We define a wave as a disturbance moving through a medium. A wave is a disturbance moving through a medium. That sounds very technical, so let me take a moment to explain it to you. So first of all, a disturbance is something that interrupts something. If your little brother or sister disturbs you, they have interrupted you. So you can see in our examples of waves with people here that that disturbance is like an interruption. They were doing something. In this case, they were crouched down. In this situation, they were standing up. And now they've been interrupted and they're doing something different for that one moment in time. And then the thing that the wave travels through is called a medium. So we use that word medium here, not to talk about small, medium, and large sizes, but to talk about what the message is being passed through. So for example, an artist can use different mediums to pass along the message they want to share with the world. So an artist might use the medium of paint to share their message, or they might use clay or sculpture. And the thing that they're using to pass their message along, the material that their idea is passing through, is called the medium. So when we talk about waves in science, the medium is the solid, the liquid, or the gas that this sound is traveling through. So in this case, our medium for this wave is people. But we have looked already in class at examples of waves traveling through other things. So the medium of a solid, we looked at our Chinese water spouting bowl as an example of sound traveling through the medium of a solid, brass. We know that sound can travel through liquids, like the water that we saw with our tuning forks. So liquid can be a medium. And then finally, we also know that sound can also travel through gases. That's how we're able to hear things. So of course, when sound travels through air, we can't see it traveling, but we certainly are able to hear it because of that. So more about sound waves specifically then. Sound waves are a type of wave called a compression wave, And a good way to think about that is actually an earthworm. So if you watch an earthworm move, the way it works is he stretches his body out, and then after he's stretched out, he kind of presses and pulls parts of his body back together. And he does this stretching out process and then a pulling together. So that is really kind of how a sound wave moves through a medium, is that same idea. So we have a compression part and then a spread apart. So if you look right now, this part is a stretched out section. And then looking at where my pointer mouse is, now it's being compressed together. Another word that we use for a sound wave, in addition to calling it a compression wave, we can also call it a longitudinal wave. Longitudinal wave. And we used our slinkies out in the hallway to demonstrate this idea. Longitudinal just means that the medium, the solid, liquid, or gas, is moving in the same direction as the energy is. And so I had you actually look at the slinky and look at the individual coils of the slinky, and you can see that the wave is moving from left to right, but also the slinky coils are moving from left to right as well. So that's what we call a longitudinal wave. When we study light, we'll look at how light is actually a different type of wave. A light wave goes up and down in what's called a transverse wave. But for sound waves, they are called compression waves, or they're called longitudinal waves. And this gives you another demonstration of that to just kind of help you understand it. Sound waves move outward from a source through a medium. They move outward from a source through a medium. So here we have a speaker that's vibrating. And I love the way that this one really shows you what happens with the air molecules. You can physically see how that speaker, as it vibrates and moves back and forth, it's actually pressing together the air molecules that are right next to it. And then that pressed together energy moves on through the wave. You can see the same thing here with our tuning fork. But I do want to point out that if you look at these little red dots, those red dots are individual air molecules, or they could be water molecules, depending on what the sound is moving through. Those individual little molecules, though, they don't go the entire length of the wave. It's not like a water or air molecule that was right next to the speaker is going to end up all the way across the room on the other side as the wave passes through. Instead, those individual little particles, those individual little molecules, are just going to like kind of move forward and then right back to their spot as they pass the wave along. So let's take a look at the parts of a sound wave. And these 4 vocabulary words are really important because we're going to use them throughout the rest of our unit to help us better understand why we have different types of sounds. So first, anytime you have a sound, there's got to be some type of source of the sound. That's where the sound wave starts from. And you know that because anytime you hear a sound, usually the first thing your brain is thinking is you turn your head because you're trying to figure out where the sound is coming from. And you're looking for the source. What is it that's vibrating, that's starting the sound? And then as the sound travels through a medium of a solid, liquid, or gas, air, water, whatever it is that it's moving through, the part of the wave that where the molecules are pressed together is called the compression part of the wave. That's why they're called compression waves. So compression is pretty easy to remember because it's where the molecules are pressed together or squeezed together. So compressions in this illustration would be here, 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 and here. Those are compression parts of a wave. And then the part of the wave where the molecules are spread apart is called a rarefaction. It is one word, rarefaction. Faction actually means a part of something, and rare would mean not very often or spread apart or unusual. So the part of the wave where the molecules are spread apart, where we don't have that many air molecules, is called the rarefaction, and that would be here, 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 and here. Let me show you a moving illustration of that with air molecules so you can kind of get an idea of that. We have our source, and then the rarefaction is where they're spread apart, and then the compression is where they're squeezed together. And again, if you looked at any of the particles, the little red dots, you can see that how individual air molecules don't actually travel the whole way down the wave. They just pass the energy on, as our rarefaction and compression, though, follow the length of the wave. Here's another illustration of that same idea, just a slightly different picture of it. So you can see your compression and rarefactions. And the compressions are all the places where it's squeezed together. The rarefactions are all the parts where it's squeezed, where it's separated or spread apart. And then the very last part of a sound wave, we've looked at source, compression, and rarefaction. The last one is one that's really going to be important for the labs that we're looking at and helping us better understand how we have different sounds. And that is called the wavelength. So here it is right here, the wavelength. And that is the distance between two compressions. So wherever two compressions are next to one another, the distance between them, how far apart those compressions are, is called the wavelength. And so if you look at different sound waves have different wavelengths. If the object is moving quickly, then over here we're going to have short wavelengths. So there's a whole lot of compressions happening one after another on this side with the short wavelength. If the compressions are farther apart from one another, we have a longer wavelength. There's more distance between them. And here is one more illustration of that, having shorter wavelengths and longer wavelengths. And like I said, we're going to do some labs that will help us better understand the difference between those.